I now call to order the Society's 2,449th meeting in the 150th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein, as most of you know. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Bob Byer. The Society has been meeting and hosting lectures via Zoom for over a year, starting with the Joseph Henry Lecture on May 15th, 2020. And it is nearing 2 years since our last in-person meeting on February 21st, 2020. I am therefore delighted that today's meeting is being held in person at the Cosmos Club, including a pre-lecture reception and dinner with our speaker, and that we currently plan for our next 2 meetings to be in person here at the club with our speakers, Francisco Cordova of the Arecibo Observatory, and then Sean Andrews of the Harvard-Smithsonian Observatory. Beyond that, we will take it 1 meeting at a time, although we hope to continue meeting in person regularly. All in-person meetings will adhere to the COVID-related rules of the District of Columbia and the Cosmos Club. Proof of vaccination, including a picture ID, will be required for in-person attendance. And masking, except when eating or drinking, and being the speaker, will be mandatory. Additional details will be posted to the PSW Science website. Please check the website often for up-to-date information. Of course, we will continue to live stream the lecture proceedings to YouTube for a remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the live stream recordings will be posted to the PSW YouTube channel and the Vimeo channel, where they will be permanently available to everyone to view without charge. Speaking of videos, it's worth noting that PSW has posted 170 videos to the PSW YouTube and Vimeo channels. They have been viewed on YouTube well over 500,000 times. Viewers have spent almost 100,000 hours viewing each of the 2 most popular videos, both on physics, of course, and more than half of the viewers are located outside the US in more than 50 foreign countries. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who asked to remain anonymous. I am pleased to announce the following new members: Rami Schwartz, a writer and entrepreneur with youtube.com and your.tube, interested in journalism and philosophy, and learned of PSW from the web. And Bob Byer, tonight's speaker, whose interests will be clear to you in part from tonight's proceedings. We welcome them to membership. If you are not a member and would like to join or support the Society, you can do so through the PSW website. Just go to www.pswscience.org and look on the homepage for the blue join button at the upper right-hand corner and follow the prompts. We welcome new members. Recording Secretary James Heelan will now read the minutes of the 2,448th meeting and the lecture by Romy Amaro on computational microscopy of SARS-CoV-2, using simulations to see the unseen. James.
Thank you, Larry. Good evening, everyone. It's really great to see you here. On November 5th, 2021, by Zoom webinar broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,448th meeting of the Society to order at 8:02 p.m. Eastern Daylight Time. He welcomed new members, and the acting recording secretary read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Romy Amaro, president and endowed chair in the Department of Chemistry and Biochemistry at the University of California, San Diego. Her lecture was titled Computational Microscopy of SARS-CoV-2, Using Simulations to See the Unseen. Amaro's research group, among others, has developed a technique called molecular dynamic simulations, which she characterizes as a computational microscope. The technique uses computing to synthesize diverse data sources to produce detailed three-dimensional models of biological systems that are then brought to life by using basic laws of physics. Her group has used this technique to use different structural data sets with glycomics to approximate the SARS-CoV-2 system and reduce it to basic mechanical elements. By then applying Newton's equation of motion, Amaro's group builds a dynamical understanding of the system's movement over time. In February 2020, the product of 7 years' research, Amaro's team presented a paper on molecular dynamics simulation of the outer envelope of the influenza virus. Contemporaneous with that publication, a research collaboration with the U.S. National Institutes of Health published the first cryo-electron microscopy structure of the SARS-CoV-2 spike protein. Amaro then described that structure and its modeling in detail. Spike proteins sit on the virus surface, and thus are the first contact the virus has with human cells. By using their computational microscope to fill in gaps in the NIH team's model, Amaro's team was able to see the protein's complete spike structure and its membrane composition. The speaker then showed a slice of the membrane that her team modeled, illustrating the cytoplasmic tail that sits inside the membrane. She then showed and described animations of the virus structure subjected to Newtonian physics. The simulation showed significant wiggling and jiggling, explaining why crisp imagery of the virus proved so elusive. Amaro said that while images were computationally expensive, they allowed researchers to compute properties that link directly to lab-testable experiments. From these experiments, scientists were able to confirm what the full-length, fully glycosylated spike protein looks like, including sugar linkages that scientists could not previously see. Amaro then detailed their specific findings. This information is crucial for SARS-CoV-2 vaccine and drug design. In the absence of conferences, Amaro said that social media quickly became the means through which she communicated with other scientists about the research. By Twitter, she was able to meet Alyssa Fada of Maynooth University in Ireland, with whom she collaborated to develop an experimentally testable hypothesis that SARS-CoV-2 glycans had purposes beyond shielding. Also by Twitter, Jason McClellan, co-inventor of the Moderna vaccine, responded to one of Amaro's spike protein videos. As a result, McClellan's lab developed a biointerferometry assay that showed spike protein mutations supporting Amaro's hypothesis that the virus's glycans participated in the mechanism of infection. The speaker then described her team's work on the fusion of the virus's two membranes. They partnered with Lillian Chong at the University of Pittsburgh, who developed a method called weighted ensemble molecular dynamics. The method is a statistically rigorous way to overcome the computing barriers to standard molecular dynamics and simulate the virus's spontaneous membrane opening. Whereas standard molecular dynamics would take more than 800 years to determine one pathway, Chong's method accomplished 310 pathways in 23 days. These weighted ensemble trajectory simulations are in agreement with the manifold EM results of PSW member Joachim Frank's laboratory, conducted by graduate student Evan Seitz. The resulting conclusion is that a glycan gate controls the opening of the SARS-CoV-2 spike protein. Amaro also studied the ACE2 receptor. Her team found the receptor was surprisingly flexible, facilitating the mechanical process of membrane fusion. The dynamics developed from the weighted ensemble simulations have now been fed into a deep learning method to make simulations more efficient. Experimentalists have since uncovered SARS-CoV-2 morphology, including the size of the membrane envelope, and both the number and distribution of spike proteins on the surface of the virus. From those findings, Amaro's team has been able to simulate methods for building the virus's membrane envelope. Her laboratory's work has now been recognized by the Gordon Bell Special Prize for High-Performance Computing-based COVID-19 research. Ongoing work continues through worldwide collaboration and information sharing using freely available open access community software. The speaker then answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 10:23 p.m. The temperature in Washington, D.C., 10 degrees Celsius. The weather, clear. Number of concurrent viewers on the Zoom and YouTube live stream, 46. And views on the PSW Science YouTube and Vimeo channels, 189. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. For those of you who missed it, I commend the video of Romeo Mauro's talk to you. It is truly a spectacular talk with some of the most amazing graphics you're ever going to see. Graphics that took supercomputers a lot of time to render because they're atomically precise. So by all means, the minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. We now turn to tonight's lecture on Microchip Accelerators, laser-driven particle accelerators on a chip. It's my pleasure to introduce tonight's speaker, Robert Byer. Bob is Keenan Professor of Applied Physics at Stanford University. He's had a very distinguished career. At Stanford, among many leadership roles, he has served as Vice Provost and Dean of Research, as Chair of the Department of Applied Physics, not once, but twice, and as Director of the Ginston and Hansen Laboratories. He's also served as President of the American Physical Society, President of the Optical Society of America, now known as Optica, as a member of the Air Force Scientific Advisory Board, and he was a founding member and chair of the California Council on Science, among other prominent roles in public and professional service. Bob's research focuses on lasers and nonlinear optics. His current research projects include the development of precision laser measurements to support the detection of gravitational waves and the development of laser accelerators on a chip. He's an author on more than 550 publications, and he has given many, many talks at technical conferences and to more general audiences. Bob is a member of the National Academy of Sciences and a member of the National Academy of Engineering. He is a Charter Fellow of the National Academy of Inventors and a Fellow of the AAAS, the American Physical Society, the Optical Society of America, and the California Council on Science and Technology. He is the recipient of too many prizes and awards to enumerate them here, from professional organizations including IEEE, OSA, APS, and AAAS. He earned his BS in physics at UC Berkeley and his MS and PhD in applied physics at Stanford University. All questions will be fielded after the lecture during the Q&A session. Please join me in welcoming Bob to the stage. Bob?
Okay, so this evening I'm going to take you on a little bit of historical tour about accelerators and focus on Accelerator-on-a-Chip, which is an international collaboration of scientists from Asia, from the United States, and from Europe. And I hope get you excited about some of the things that we can do with an accelerator made 10,000 times smaller than the SLAC accelerator. So I'll start by saying that one of the mantras in my research has been a statement by Edwin Land, who invented the Polaroid camera. He also, of course, left Harvard before he graduated in order to found a company called Polaroid, which made Polaroid films for World War II. Never undertake a project unless it's manifestly important and nearly impossible. Now, we tell the graduate students, of course, the project is manifestly important. They know that. But we never tell them it's nearly impossible. Okay? So they learn how hard things can be sometimes. All right, let's see if we can get this to work exactly right. All right, I'm going to show this now rather than later because I'm worried that it may or may not show. This is a video prepared by the Leibinger Foundation. It was shown for the first time 2 weeks ago when the A-CHIP program was awarded a Leibinger Prize for innovative technology in Europe. And so here are the two PIs of the project, Peter Hummelhoff and Bob Byer, and let's see if it starts. Yes, okay.
Hey, Bob, Peter speaking.
Hi, Peter.
The film team was here. It was quite a show. Yeah, they want to know everything.
Did you dress with a coat and a tie or a little more summer casual?
I indeed dressed with a coat and a tie.
Now I put a tie on because Peter Hummelhoff said he wore a tie during your interview. Otherwise, I never wear a tie.
Robert Byer and Peter Hummelhoff, two physicists, two continents, one mission: to reduce the size of particle accelerators by a huge factor, using laser beams.
Hearing particle accelerator, many people probably first think of those huge machines at CERN, of the large research-driven machines that make it possible for us to explore the very essence of matter.
Not many kilometers long, but centimeters short. The goal, the miniaturization of a particle accelerator to chip size. Now, that sounds a bit like science fiction.
Small is beautiful, and building an accelerator on a chip sounds like it's impossible. But we combine the tools of the semiconductor industry with modern lasers and can build a laser-driven accelerator in a transparent dielectric.
Friedrich Alexander University in Erlangen, Department of Laser Physics. Peter Hummelhoff and Robert Byer are head of the international collaboration A-CHIP, or Accelerator-on-a-Chip.
The beam passes through here. We can look through this structure along the line of vision. The electrons passing through here are accelerated because this structure shapes the laser light into the proper form. And this is the accelerator we build on a chip. That model is then lithographically fabricated on a scale that is smaller by a factor of about 1,000.
The electrons propagate along the special nanostructure.
So we've added little bells and whistles to make these structures more effective so that we can use intense laser radiation to accelerate the electrons.
These pillars are simply there to help us to generate the field, the optical field, in such a way that the electrons are accelerated as efficiently as possible.
First, we need a source of electrons, and in our case, that's an etched tip of silicon. Then we need a way to get those electrons pre-accelerated, and we do that in a buncher at pre-accelerator stage. And then finally, we have the acceleration stage to gain more energy for the electrons, which is useful for applications.
The innovation harbors enormous potential for fields like materials science and physics. A new generation of nanophotonics-based particle accelerators in the making.
What we have here is the core piece of our setup. The electron microscope is simply the source of electrons. Our little accelerator chip, where we accelerate the electrons, is inside the electron microscope. When the electron pulse arrives, the laser pulse is directed onto the chip and either accelerates or interacts with the electrons.
The technology is compact, versatile, and easy to scale. A huge breakthrough for Bob Byer of the University of Stanford, who has been working in this area for decades.
This program is funded by the Betty and Gordon Moore Foundation, and it's enabled us to do a nearly impossible but very important task of building the world's smallest accelerator.
A dream come true for the two researchers. Things could have turned out quite differently.
As a small boy, I wanted to become a captain on a rescue lifeboat. But then we took a boat to Helgoland in stormy weather. I spent most of my time feeding the fish, which forced me to rethink that idea.
Lucky for science, Bob was planning to become an astronomer.
My grandfather worked on the Palomar telescope and on the Mount Wilson telescopes as a machinist. So he introduced me early on to telescopes and being able to go up the mountain to the telescope.
Now he has gotten his grandkids interested.
I looked at the rings of Saturn the last time.
Wow, that's neat.
But away from the cosmos and back to the nano world, the scientists believe that there will be applications in medical therapy, a very important field for Bob Byer.
we can make an accelerator small enough that you could insert it in the body and do your irradiation on the tumor directly and not put radiation anywhere else in the body. And that would make a big difference for patient health and patient recovery. So that's one of the long-term goals, is to have an accelerator small enough that medical doctors would have it in their home office and could use it for treatment.
But there is still quite a way to go until then. The current setup looks like this.
This is what we promised our wonderful financial backer, the Moore Foundation, a machine that is the size of a shoebox but can generate high-energy electrons.
And we chose Peter Hommelhoff's foot because he had the biggest shoe.
80. We've achieved 80%. It probably does warrant the term game changer because we are actually able to shrink a standard accelerator by a factor of 10,000.
Peter Hommelhoff and Bob Byer, they may have lots in common, but there is one minor difference.
It hardly rains in Franconia, until it does. However, this is the driest region in Germany.
It never rains in California.
Okay, that's an after-dinner treat. One of the things that we learned from working together is that we both have fun doing science, and building a team together for the HIP project actually was an exercise in making friends around the world. So now let me go into some of the details of the story, but since you've got the overview, and you actually got to see images of the lab, which is hard to do on a flat screen, but pretty good to do with a video camera. All right, so in addition to working on accelerators and laser accelerators, in the past I worked with lasers and nonlinear optics, made tunable laser sources. Our tunable lasers were used to do infrared remote sensing of molecules in the atmosphere, a topic that's now hot again. This was way back in the 1970s. We received an invitation to participate in the LIGO project in 1986. And in fact, in the end, Stanford provided the lasers to LIGO. We provided the isolation suspension system for LIGO, and we provided the optical coating technology for LIGO. So Stanford, Caltech, and MIT were the three principal universities to build the LIGO interferometers in the two locations in the United States and one location near Pisa, Italy, in Europe. Okay, so LIGO and gravitational wave process has been part of my life for the last 30 years. And of course, accelerators on a chip. So this was a Physics Today article written and published in August of this year. I show it, so if you want to read a little bit of the background, you can. It has a series of figures, and I've organized the figures so they tell a story on their own. So if you don't want to read about it, but just page through it like an anime comic book, you could do that. Microchip Accelerators was the title that Physics Today chose. We were happy with Accelerator on a Chip, but this is less words. That's pretty good. Here is an image of an accelerator designed by a special process, and I'll give you an explanation of this in a few minutes. It's called inverse design. And inverse design allows the computer to test 100,000 different designs subject to the same boundary condition. So once you specify the boundary condition and the conditions that have to be met in the modeling, the computer goes to work and does something that a human brain just can't do on the same scale. And what you see is you get objects that are other than rectilinear. We would have never come up with an object with these kind of funny shapes in our pursuit of the optimum accelerator structure, but the computer did. And inverse design is going to impact the way we do science in many fields, not just in physics. All right, I use a picture of Making Waves by Charles Townes as sort of a way to say, here's the outline of what we're going to talk about. First came accelerators and then came lasers. I'll give you a little bit of overview of the background of accelerators. We built the first laser acceleration in a dielectric structure, success. We'll talk about that. And then finally, the Moore Foundation came to our rescue and have provided wonderful people to work with and support for this program. All right, if you want to learn generally about accelerators from a point of view of the people in the field, then go read the book here by Andy Sessler, the late Andrew Sessler, A Century of Particle Accelerators. He interviewed and gave backgrounds of the early practitioners of accelerator science. And so it's a nice read because you're learning about the times, the science, and the people. At Stanford, when I arrived, SLAC was under construction. SLAC is the Stanford Linear Accelerator Center located behind campus. It's a 3-kilometer-long microwave-driven accelerator. So the first beams at SLAC were in 1966, and it was 1 giga-electron volt. So it took 3 kilometers to get a GeV of energy. I like to title it there, Ike to ask 100 million for the Stanford A Smasher. So in late 1950s, 100 million was real money. You could actually buy more than 100 houses with 100 million. All right, so SLAC was built in 10 years. It led to multiple Nobel Prizes in particle physics. And the centerpiece for the SLAC community and laboratory was particle physics for the first 50 years of its existence. And that has now changed. All right. One of the things that we did early on, joint with SLAC and with John Mady, was to investigate free electron lasers as a way to make tunable laser radiation. And this is the write-up in Andy Sessler's book about John. John died a few years ago, but he was a champion for making tunable X-ray lasers called free electron lasers. Here's the world's first coherent X-ray laser. It is a free electron laser. It occupies 3 kilometers of slack and about 120 meters of an undulator at the end, which wiggles the electrons to make them radiate. This machine turned on in about 20 minutes, which is a world's record, and it generated radiation in the 8 kilovolt, 8 keV photons of X-rays, and it generated a millijoule at 10 hertz, or about 1/10 of a watt at average power. This is an extraordinary advance, and it brought for the first time laser-like radiation into the X-ray spectral range. But you notice it doesn't fit on a tabletop or a desktop. So one of my goals from the very beginning for the A-chip program was to build an accelerator that's not 3 kilometers long, but on the order of 1 meter long, and use that small accelerator to drive a free electron laser on the tabletop. So that's been one of the goals of this program. But I thought you'd like to see the free electron laser at SLAC. It was the world's first such X-ray laser. All right, what about accelerators? Well, I should tell you a few words about accelerators to get everybody on the same page. An accelerator is just a transformer. That's Pete Panofsky, the godfather of accelerators, trying to tell somebody that if you plug a transformer into the wall, it will take your 110 volts and you can amplify it up to 110 kilovolts if you wish. That's a transformer. All accelerators operate at the damage limit. When Pete told me those words, I responded, so do lasers. We turn up lasers until we damage them. To be an efficient, an accelerator must operate in reverse. Well, that means if I run it backwards, it should be as efficient as if I run it frontwards. And when you run an accelerator backwards, you take bunched electrons and convert them to light, to radiation, to X-rays. And Bob Seaman, my colleague and really an accelerator scientist, an accelerator requires structured matter, a waveguide to efficiently couple the laser field or the microwave field to the accelerator. And here are the components of the accelerator: an electron source, a pre-accelerator with DCR and an RF modulator buncher, the pre-accelerator, the accelerator structure, and then you can add on that an undulator to make radiation if you wish. And all of this is in a very straight line, and the electrons follow that straight line. To give you an idea of how long we've been thinking about this problem, I have down here in the bottom line, 1974, sabbatical leave in Lund, Sweden. I spent 3 months in a very cold and snowy Sweden studying laser accelerators. 20 years later, 1994, SLAC invited me to give a presentation at the SLAC Summer School on progress in laser accelerators. So that was the reconnection back to SLAC. That led to a collaboration with SLAC that's still ongoing. And then in 2004, 8 years after we started working on laser acceleration, we had our first successful experiment. I went through that explanation because we as scientists often do not communicate to the public how long it takes to have a major breakthrough in science. An accelerator on a chip was not ready to be developed 20 years ago. It may not have been ready to be developed even 10 years ago, but after 30 years of thinking about it, we think we're on the right track. So it takes time for these new ideas to come to where they can be reality. All right, lasers. I grew up in Southern California, and Malibu Beach is my surfing spot. And in 1960 was my last summer of surfing before I headed up to Berkeley to study physics. And just up the hill from Malibu Beach was the Hughes Research Labs where Ted Maiman made the first ruby laser. And you notice the ruby laser was powered by a flash lamp, a discharge lamp. And the early lasers came that way. Most of the early lasers were gas discharge lasers, not very efficient, and they were hard to scale to any average power. Because the laser was invented, scientists around the world began to think, could I build a laser accelerator? And this is one of the earliest papers by Koichi Shimoda in Japan. Here's a paper by Rosenzweig at UCLA, and Byer group at Stanford worked on another part of this. So the idea was there, but it was too early to take it on and do something about it. All right, so comes 2011. Darpa knocks on the door. We've worked with Darpa before. They're a tough customer. They want you to do the impossible without any money, and they want you to do it tomorrow. And that gets to be pretty hard to do in fields that don't move that fast. So when Darpa came to us, we said, yes, we would take on their challenge to work on a laser accelerator, but they had to understand it would do them no good to cut our budget in half and cut our time in half to finish the project. It just wasn't possible in accelerator science to do that because like a telescope, you sign up for time on an accelerator. You may get a week in 6 months, and then you get another week, and that means you progress pretty slowly. So this is a group that worked on the Darpa project. All of us were a lot younger then, 2011. We built an accelerator about the size of that chip. I carry one in my pocket. I have it here. And we needed a source of electrons to drive this accelerator. And the source of electrons is on the left. It's the Next Linear Collider Test Accelerator in LCTA. And it's located at SLAC. So SLAC gave us access to that accelerator, and we could use it to put electrons into our small itsy-bitsy little accelerator. We explored at SLAC a whole number of different types of accelerators, fiber accelerators, planar waveguide accelerators, silicon log pile accelerators, and periodic phase reset structures, which is in the upper right-hand corner. I'm going to focus on periodic phase reset because that describes basically what we're doing now. The other types of accelerators have been explored, but at this point, they don't show that much promise. All right, so here is a Zig Zag structure and made out of quartz, glass. The laser beam is focused into the structure from the side, and the electrons start at the bottom and run down the structure. So that's the kind we built. We turn up the laser field until we get right to the damage limit of the fused silica structure. At the damage limit, the electrons are pumped and can gain about 2 billion electron volts per meter. If you load this structure, it drops down to about 2 GeV per meter electron energy. That's the gradient called the acceleration gradient of the accelerator, and it tells you how long the accelerator must be in order to get to a given energy. And this is pretty high. SLAC typically runs at 30 gigavolts per meter, 30 megavolts per meter. And so it takes 3 kilometers of SLAC to get to on the order of 10 gig electron volts of electron energy. We think we'll be able to do the same thing in about a meter of laser accelerator. All right, so we're interested in putting a high electric field on structures. To do that, we need to measure the damage limit of structures. So we used a Ti-Sapphire laser and a picosecond pulse. And we measure the damage of quartz, SiO2, which is glass, silicon, which is down here at 0.19. And here, if you build the accelerator out of metal and try to pump metal with a laser, you don't get very far because metals absorb laser radiation and they damage quickly. So we chose to work on two materials. One of them is fused silica, SiO2, and the other one we work with is silicon. And even though silicon has a much lower damage threshold, it has some redeeming features, like we know how to engineer the heck out of silicon. It's been studied and engineered by people for decades now, so we could probably do something in silicon we can't do anywhere else. So that's the measured damage thresholds. Edgar Peralta came to my office one day, knocked on the door and said, I want to work on accelerators. I said, what would you like to do? He says, I want to build the structures. I said, okay, go ahead. 5 years later, he finished the structures and they worked and he graduated. He was my first student from Columbia, South America, as the first of a group of students that are coming north now to go to school for their PhD. And Edgar did a really good job because his structures that he designed and built and then tested are still being used and still being tested. All right, there's a photograph of 240 accelerators on a wafer of fused silica. They reflect light because they're gratings. They're meant to reflect visible light. We've typically built 4 accelerators on a little strip. We harvest that strip with 4 accelerators, and then we have to put it in front of our electron beam and get electrons to go down the small holes, and we have to pump it from the top with a laser beam so we get the laser accelerating the electrons. So here's what it looks like under an electron microscope. You see that it's a 400 or 800 nanometer wide gap for the electrons to go through. That turns out to be very hard to do. And but other than that, it's just a modulated structure to make sure the electric field gives the most acceleration gradient that we can get. All right, and we then take that accelerator, which is in the circle in the middle here, put the electrons in, turn on the laser, pump it up, and use a magnet to measure the electron energy and display the field on scattered electrons on a fluorescent screen. The experiment's conceptually very easy. It turns out in practice it's really hard. And the reason it's hard is the electrons come in bunches of 30 micron, and we're going to try to put them down a half a micron line. So it turned out we were not very good at that for a long time. I want to do this. There we go. Okay. So right there is the big hole that we start with, and we work our way down the smaller holes. And by that time, we're lined up close enough to get through the grading structure. I have a visual cue of how hard this alignment is. Here's the 30 micron 1-to-1 aspect hole. There's the size of the electron beam at best focus. 10-to-1 isn't so bad. 100-to-1, we can usually get the electron beam in less than a day. This is what we're trying to do. We're trying to get the electrons down that very skinny 540 optical cycle long, 0.5 millimeter accelerator structure. That typically took about a week to get that alignment done. So when you get 2 graduate students that are smiling from cheek to cheek, and it's 4:05 in the morning at SLAC, right? 4:05 in the morning, go graduate students. They're happy. Why are they happy? Behind them, for the first time, they see accelerated electrons. These guys are in phase with the laser field and are accelerated. These electrons are out of phase and are being deaccelerated. And this was the first really good measurement that we could accelerate electrons in our structure. All right, and we accelerated up a gradient of 300 MeV per meter, which was outstanding. The timing had to be good to a picosecond. And when everything was all working, this experiment was an outstanding success. We submitted to Nature. Let me see, I'll take it back. We submitted the paper to Science because I was in the American Physical Society at the time, and I was trying to tell my students we owe it to the professional societies to publish in their journals. So Science Magazine reviewed the article and sent back a reject. In fact, the reject was from the editor-in-chief. So my students said, well, gee, why can't you appeal it? I said, what am I going to appeal? I usually would appeal to the editor, then the editor-in-chief. If the editor-in-chief has already rejected it, it's over. We're not going to publish in Science. So I said, and since you guys submitted to Society's journal first. You can submit wherever you want to second. So they went to Nature. And they learned their lesson of how hard it is to write a Nature article, which is basically a newspaper ad for the science. All right, so we got our article written. Peter Hommelhoff had success in the same time frame. He and his colleagues in Germany were doing pretty well. And they submitted a paper to PhysRev Letters, American Physical Society journal. And when Nature learned that this was going to be published before their article, Nature moved our article forward to match the publication date of this. I just couldn't believe that magazines or journals do this, but that's the kind of life they live. All right, so we had 2 papers simultaneously published on laser acceleration success. What do you do with that information? Well, we took it to the SLAC public relations guys, and they named it Accelerator-on-a-Chip. So that's a name from the public relation guys, not us. We were more complicated. We added the word laser and some other stuff. All right. That was a home run. So I told my students, if you're really lucky in science and it's a slow news day, there's no news at all, then your science can get picked up and published. So here's what happened. Wow, it got picked up around the world and got published in a number of different places. Oh, that's good news, a little bit of luck. And so there's the Stanford seal up there. All right. And here was the article I most appreciated by The Economist. So there's a 1-page article on this device in The Economist magazine in 2013. Our accelerator is the little teeny one, the teeny tiny accelerator down here. That's what we're working on. And the big one behind it is the normal everyday accelerators. It was a well-written article. The science was done correctly, worth reading. All right, we went then and had a beer. Peter happened to be in the Stanford area that weekend. So we went up to Rosati's and celebrated that we had 2 papers, a successful program in laser accelerators. All right, what happened next was a little surprising, but I'll hold it here and just tell you. The Friday after we had success in the lab and we knew our accelerator worked, Darpa called and said, we're canceling your project. And literally an hour later at noon, I got a telegram from these guys saying, we've canceled your project. I said, we were the only group that you funded that actually met our milestone. Why are you canceling us? But you don't argue against DARPA. They go their way and we went our way. The good news was that publicity had managed to cross the desk of the Moore Foundation, and Moore Foundation program manager Gary Greenberg visited my office a few weeks later. And Gary knew more about my funding situation than I did. And he noted that I was out of money. We'd had success in the lab. Maybe we should look for another sponsor. And I said, yes, please. And so we met with the Moore Foundation. Peter came over. We had a nice conversation. And we had a choice. Either do a small program with Peter's group and my group and leave it at that, or try to make a bigger footprint, a bigger impact by making it a collaboration that's on a global scale. And so we elected to go with a collaboration model. My only constraint was I said I didn't want to become a manager. I wanted to remain a scientist. So if we do a collaboration, it's going to be a research collaboration, not an engineering development collaboration. So it was. So that's what old accelerators look like. That's what the team that met for the first time, we met on October 2015. Faculty members at Stanford and elsewhere, scientists, engineers, graduate students, and my colleague, Yelena Vukovic, is in the back row there. And she is also, at that time, she was 7 months pregnant with her daughter. So we're going to have a baby as part of this project, too. That's neat. All right, that's the first meeting of the group. Here's the 2 co-directors. What are we wearing? We're wearing this white badge. What is that? That turns out to be a silicon accelerator. So we made for everybody that attended, we gave them their own accelerator, put it on the badge, and they could wear it. So Peter and I are the co-directors of this project. You can hear from the little video, we have a good time. The Moore Foundation did not have anybody on board who could help them evaluate the progress we would make in accelerator science. They suggested we form a science advisory committee, which we did. And Chan Joshi, who's a plasma accelerator scientist, was our advisory board chair. Reinhard Brinkmann from DAISY in Germany, and Tor Robenheimer from SLAC are all accelerator scientists, and they gave us incalculably good feedback. They were a really very important part of this program. So now you see it's organized around technical progress, technical areas. It's got an advisory board. We look like we're off and running. SLAC made available the NLCTA accelerator, so we could do testing there. UCLA had its own accelerator that they could work on, so we at least had access to electrons. All right, so one of the first experiments we did was to take Peralta's fused silica structure at UCLA and rerun the experiment to see how much acceleration gradient we could get. And in that second experiment, we went from 300 MeV per meter to 690 MeV per meter. So it showed a lot of promise. I'm going to skip that. Okay, here we go. We had our meeting, off-site meeting at UCLA at the time down when we were just starting in the program. This is 2016, 1 year into the project. Here's an idea of an accelerator. We have a point source of electrons. We have a pre-accelerator and a buncher. We have a speed of light accelerator. All of those things have to work together, and they all have to work in the proper phase. And so if you build it up, the electrons that are going down this very narrow channel will stay within the channel if you provide some means of focusing. You must provide some means of focusing, or the electrons will spread out, crash into the walls, and be lost. So here is the structure we eventually derived that does this periodic focusing down the accelerator structure. We can then think about coupling light from off the chip onto the chip, and then use guided waves on the chip to drive the accelerator. All right, so here are all the elements. So the project basically is an accelerator science project. We're trying to take all the known aspects of a linear accelerator and reinvent them so they fit on a silicon wafer. That's the goal. Whether we could do that or not was not known when we started. I mean, we didn't even have a source of electrons, so we were really worried that we would never get a good source of electrons that would fit on the silicon wafer. So those are the elements of the accelerator we need. If you want to make an X-ray laser that goes on the tabletop, you need the undulator, which is also driven by the laser, just like the accelerator. All right. If you want to read about the elements of a dielectric accelerator, Josh McNewer and Peter Hommelhoff have a nice article. Let me give you some idea of the kind of work that goes on in order just to make a little progress forward. We need a source of electrons. And the most likely source that we had available was a tungsten tip, because Peter Hommelhoff had worked at Stanford as a postdoc on tungsten tip sources. So we worked on tungsten, we worked on lanthanum boride, diamond tips, working with Los Alamos, and silicon nanotips. So the last one to the far right is silicon. All of these had reasonable lifetimes, but not super long. So they were mostly pretty efficient. We used a laser to pull the electrons off the tip. The one that won the day by surprise was silicon. It turns out the silicon tip, if it's annealed by the laser, if it's heated enough to melt and re-solidify, becomes a very good emitter. And it's a very strong emitter that doesn't die. So we get weeks of operation time with a silicon tip as a source. We didn't know that when we started the project. We had no idea silicon would be a tip of choice, but we were glad it worked out because it fits into the lithography perfectly. All right, here's the first silicon accelerators by Ken Liedl. It's a Ken Liedl idea. He wanted to design an accelerator that did not require that you flip the chip bond, and he made them out of silicon. In order to test them, we borrowed an electron, TEM electron column. They're the source of electrons at the top, and the electrons go down the channel. This was a piece of used equipment from Professor Fabian Pease. We say thank you to Fabian for loaning us his electron beam column and for giving us lab space for a couple of years when we had no place at Stanford to work. We were able to do experiments in the Fabian Pease lab. All right, so here's the first publication on silicon, 370 MeV per meter. on a silicon dual pillar structure. What do we mean by dual pillar? We mean that these guys, those little pillars there, are what modify the incident electric field, and the electron runs right down between them and gets accelerated. We use a magnet to resolve the energy of acceleration and go to a camera to see the results. So here's a close-up of these silicon pillars. You don't have to put anything on top of it because you let the electrons run right there. Okay. So the electrons run down from the top of the pillars, and when they do that, they get modulated, and they can either be driven by in-phase laser light, which gives you a beam steering, or if it's out of phase, you can get focusing or acceleration. So these are Cauchy and cinch functions, so that's the highest mathematics I'll go tonight. So these pillars resolve into modes, and the acceleration mode will accelerate the electron and focus it as it goes along. These are built on a silicon wafer. We typically build them 10 or 20 microns above the base of the wafer so we don't get scattered light everywhere. And they work extremely well. I don't want to go backwards, I want to go forwards. So there's the electric fields that are calculated and plotted out. We can change the phase of the laser, and if we do that, we can rotate the acceleration gradient. So we can deflect in the left, we can deflect to the right, we can focus all in this very simple silicon structure. We can focus, turns out that's absolutely crucial. So there down at the bottom left are the DLA structure and an aperture to measure how tightly we focused. And we can also focus by doing something else. We can change the shape of the teeth of the grating, and that makes a focusing element. So we have two different ways to focus the electrons, which is important in the future. These focusing elements are basically driven by the magnetic field component of the laser radiation on the accelerator. And these quadrupole lenses have megatesla per meter magnetic field gradients, much higher magnetic fields than you would get from permanent magnets used in classical undulators. Finally, we have to learn how to put the light into the electron bunch such that they get continuously accelerated forward. And this is a PhD thesis result from Tyler Hughes. He developed this sort of tree structure for taking the light that comes in and feeding it down so that it stays synchronous with the electron bunch as the electron bunch moves along. That was a tour de force, a very difficult and long-term analysis to get it right. All right, where are we now? Well, we can make structures, and like this one, they're quite pretty. This is the winner of the SEM image competition in Europe by Peter Hammelhoff's group. And you can see that it's very clean structures, very interesting to work with something that's so easy to build on silicon and do it so cleanly. Here's another advantage. We can build a mirror behind the accelerator column. That's a Bragg mirror, and we can reflect laser light back on itself, so we double the amount of electric field that the electrons see. And we did that experiment, and down in the bottom left, we show that we almost double the acceleration gradient by using this built-in mirror. Now I'm going to take a jump into something totally unexpected. Not expected by me, not expected by my colleagues, but probably known by Yelena Vukovic and Shanhui Fan. It's called inverse design. So inverse design means I lay out the boundary conditions of what I want to build, and I put some other constraints like the minimum spot size my structure can make. And I let the computer go to work, and using gradient descent, the computer calculates the optimum structure for what you're trying to achieve. That's called inverse design. And so these show some of the outcomes of inverse design on the right. You see these sort of circles and elongated structures. These are beam splitters, but we would have never designed these beam splitters starting with pencil and paper. There's just no way my brain would ever work in that kind of geometry. We're often asked the question, how do you know they work? If you can't explain how they work, how do you know they work? We put them in the laser beam, and away we go, and they work. All right, so inverse design was applied to the accelerator. There's Yelena Vukovic and And the first structure that it predicted was what we call a sine wave structure. And that's something we had analytically done through the human smarts. And both solutions agreed and said this would work pretty well as an accelerator. The one that I like is the one that was published in Science magazine. Sorry, I'm not holding the microphone up. I need a lapel mic. Thank you. This was an article published in Science. Remember, it's the infamous Science magazine that rejected our first paper, right? So when Neil Sapra, the student, said, I'm going to submit this to Science, I said, we already got rejected by Science. Why do you think they're going to take it this time? It turned out Science in Europe has a different editor than Science in the United States. And the Science in Europe liked the accelerator projects. So he basically told the editor in the United States, hey, publish this. So they accepted the publication, and this is the world's first on-chip integrated accelerator. The light comes from off-chip, it hits a grating, goes down a waveguide, and hits the accelerator structure, accelerates electrons, and then is reflected out of the structure and away. So here's a little closer look. The N coupler is up at the top. The waveguides take it down to where you see the E minus. That's the channel where the electrons go. And then the out coupler couples the radiation out that wasn't used. And there's the ideal structure that you get from inverse design. And this is just an organic kind of picture that I would have never imagined ever seen in my life, let alone having to become part of a project where we're trying to accelerate electrons. The blue is the field intensity. The background is silicon. The electrons go up the channel vertically. So that's a surprise and a big plus for all of us. All right. So Accelerator-on-a-Chip continues. We're in our beginning of our 7th year. The Moore Foundation extended us by 2 years. One, because we lost a year due to COVID. We did lots of publications. We had 36 publications last year because you couldn't go in the lab and do work, so you wrote papers. So there's a lot of things that we have yet to do. One of them is to understand how to focus the electrons going down the accelerator. And I'm going to skip here a little bit because those are a gradient. Okay. Number one, the electrons that go down the thing ride an optical wave. They ride the front of a wave. And because they ride the front of a wave, the length of these accelerator bunches is about 100 attoseconds. The laser pulse length is 5 femtoseconds. Number two, if we want to create a short pulse of electrons, we can modulate the electrons on the left, let them drift 35 microns in free space, and then scatter them on the right on the DLA scanner. So we make a street camera, and using the street camera, we can measure the length of the electrons. So this is the world's first attosecond street camera, and at the same time, the first attosecond source of electrons. It's amazing. We get 2 groups of electrons, one accelerated, one deaccelerated. The Stanford results were about 700 attoseconds. But if we go forward a little bit, I'll go forward here. Here's the second paper. We published these 2 papers simultaneously as well, but both in PhysRev letters, one in Europe, one in the US, one in Europe. So here is the attosecond bunch train. The electrons are modulated, they drift, they bunch, and then we measure their distance. And in these, there's a structure, what it looks like. In these, the electrons got down to about 130 attoseconds was the calculated width. And we measured 270 attoseconds. This is the shortest bunch of electrons that's been generated. This is where science applications are going to lie. We can take attosecond tabletop electrons, and we can modulate the electrons to do quantum-type scattering experiments. We can focus the electrons to the size of an atom so that we'll be able to do electron-induced fluorescence at a scale in time of attoseconds. All right. The final thing was how do we get the electrons to go down along the structure? We need to focus the electrons. And our theorist in Germany, Uwe, he calculated a model that said, hey, if I can do focusing exactly right, your electrons will go down this channel, 94, 96, 98 keV. It's 100 keV, 106 keV. So the electrons are gaining energy, but they're not hitting the walls. They're staying in the middle because we have imposed on the structure alternating phase imaging. So alternating phase focusing is crucial for building an accelerator that will give you an MeV of energy. So Uwe Niedermeyer, there's the structure. We've already built the structure and we've tested it. It works. So we've solved a really key problem, and that's the problem. How do we refocus the electrons as they go down the accelerator structure? We have a 6-dimensional tracking scheme now, so we can model all of the accelerators that we want to build before we build them. And here's a short section of an accelerator showing focusing and non-focusing. And if I go ahead, here's a longer section that takes us up to an MeV. Our goal at the end of this year, maybe early next year, is that we reach 1 million electron volts acceleration in about a centimeter long structure. All right, I'm going to go through that detail because it's a little, and stop here at the shoebox. So you heard from the little video that one of our goals was to build an accelerator about the size of a shoebox. And of course, we need all the room we can get, so we took Peter Hammelhoff's shoe because he's got a big foot. So we've been working the last couple of years on building a shoebox-size accelerator. Ken Liedl in our lab at Stanford and the lab in Erlangen, Germany. We have examples of structures. This is the German model. A source of electrons, a platform where you hold the accelerator and hold the sample, and there's the total size. Not too big of a shoe, but okay. And here's the one at Stanford. We call it the glass box. It has a source of electrons, a lens to refocus, a DLA platform to put the accelerator structure, and a nanopositioning platform to put the samples. And so this all sits on our lab and our bench in Stanford, and it works. So now we're in the process of not only making it work, but making it reliable so we can do science with it. And there's a lot of work that's been done. I'm not going to go through all of that. That just tells you that it's been a busy group. They have a lot of fun working together. I hope you caught that from the video. We held our imaging meeting. Here's the real focus here. September 27, last month, month and a few weeks ago, we were in Erlangen, Germany again at the Orangerie. We held our application workshop, and these were the invited speakers. It was a smashing success. We had some really interesting talks about the application of this accelerator, primarily to ultra-fast electron diffraction, that's UED, and to ultra-fast electron microscopy of a type that was practiced by Zavale at Caltech, won him in the Nobel Prize. So that's where we are. We have a worldwide collaboration from the United States, Europe, and Asia. The collaboration is growing slowly. We're not asking it to be big, but we want to keep it effective. And we invite scientists to join us if they show an interest. Our next meeting, next March, is scheduled for Tel Aviv, Israel, where we have colleagues in Israel working on very nice applications of this accelerator. I'm going to skip through the accelerators and go to a final slide. I think you'll agree that there are applications, maybe more than we thought when we started. As far as I know, this is the first electron diffraction using our accelerator of boron nitride. We've now are entering the era of quantum electron packets. It's a hot topic right now. If you can take a bunch of electrons and modulate them properly, you can make the phase and the amplitude of that electron bunch look exactly like a single mode, a Gaussian mode of a laser beam, for example, or any other kind of mode. And we have been doing that and working with our colleagues in Israel. We use those modulated electron bunches to do scattering off of atomic systems and for fluorescence studies. So Grover and Amnon Yariv published a paper 2 years ago, year and a half ago, on free electron bound electron resonant interaction. We can write that resonance in the electron bunch and use that to couple the electron to matter. So, and finally, my favorite goal from the very beginning is generating radiation from this accelerator. We're not there yet, but there's no doubt in my mind that in a not too distant future, we'll be able to generate soft X-rays at 100 megahertz repetition rate on a tabletop that fits in your lab. And then we have access to coherent X-rays every day in the laboratory. All right, so we also know from studies we've done before that this accelerator scales. we have done the studies twice now. We've had workshops on could we ever take this huge 30-kilometer long TeV energy scale accelerator that's been proposed and convert it to something that fits on the SLAC site and does TeV particle physics studies? The answer is yes. And this accelerator handles the current density, it handles the average power. It will indeed perform quite well as a TeV energy scale accelerator. All right, let me wind up with that. That's the early group up at SLAC doing the experiments on the first runs of the accelerator. Ken Song put together this little image of SLAC on a wafer of silicon. There are the 240 accelerators that were built for our early experiments. And here's a look at the group at our meeting held in Daisy, Germany. So that's the whole group, the HIP group. Very friendly, very outgoing, very lively group. They like to have fun when they do their research. It's been a real pleasure working on the HIP project. In some sense, it's sort of a capstone or a highlight or the icing on the cake for my career to be able to work the last 7 years with this group of people and solve problems that most people thought were impossible when we got started. Thank you very much.
YouTube viewers can text questions in the YouTube chat box. These text questions will be read aloud for the speaker to hear and for everyone to hear the answer. So with that, let's start with questions. Let's start with Frederica.
Is it loud enough? I'm Frederica Derima, and actually I was at the AFOSR, and you were in the Air Force Science Board. So thank you very much for your presentation. So you talked about putting sort of this kind of, and creating a linear accelerator, replacing kind of the next accelerators at the size of SLAC, which is wonderful. But also I was wondering, have you thought about putting this in an array, and in a sense using for materials analysis, nano fabrication, and things like that? That would be wonderful, instead of having TEM, the traditional TEM.
That's a very, very good question.
Bob, could you repeat the question?
Yeah, the question was, have we thought about putting these accelerators in an array? And because then you could get parallel beams of electrons phased, and it gives you much more average power and more capability. That was the PhD thesis for Zhenin Zhao. And if I had time, I'd show you a beautiful picture of her at the Stanford Quad with her dress on. Zhenin did some unbelievably nice calculations on a phased array accelerator. And what she found is that if you pump those phases properly, they will automatically phase lock. They will stay phase locked in the accelerator. If you want put curvature on the phase to focus, you can. It efficiently couples to the optical field. And the saving grace was don't side pump it, but top pump it. And when you top pump it, it gives you the ability to extend the array beyond the 10 that she modeled. So we're quite thrilled by that, but it's buried under all the other things we've been doing. We haven't had a chance to make a highlight of it yet. We did one experiment which showed we could do multiple accelerators and they would couple, but we haven't done a full array experiment yet. But good idea.
That's wonderful.
We need you to use a microphone.
Since you are looking for funding, I mean, I was at AFOSR. We, in a sense, were looking for this kind of work. And so I don't know if you have tried AFOSR, and then also the Air Force Research Laboratories, the Materials Directorate.
Yeah, we were always looking for funding, and my colleagues who are on the line listening here will pay attention to exactly what you said.
I only make it as a suggestion because I retired as the director of AFOSR, but I know they would be interested in this work. You can contact them independently, and also the Air Force Research Laboratory.
OSR was one of our supporters early in this program. Howie Schlossberg said, if you guys are successful, this is magnificent. So he helped fund the early work that we did. And I've always been thankful for Howie. He funded a good part of my laser spectroscopy research for many years. Yeah.
Pleasure. Yeah.
Blue microphone.
Yes, my name is Scott.
If you have a question, keep your
I
hand
don't
up.
think so.
Matthews,
There we go.
and I am a member. I'm familiar with the term laser wake field accelerators.
Right.
Is this laser-driven accelerator technology related to laser wake field? And then a second quick question, which is, do you think you could use this technology for accelerating other particles, for instance, protons?
Yeah, okay, good questions. The only thing they have in common is laser and accelerator, because the wake field accelerator is basically built in a plasma structure, and the electrons ride the steep electric field gradient in the wake field behind a group of particles that went through the plasma earlier. So that is what I would call a plasma-based accelerator technology, which is about a decade ahead of where we are in the technical development, but they're still evolving to make accelerators. They have the potential for much higher gradients, but they're limited in the repetition rate because they require joules of energy to pump the accelerator. We're pumping with nanojoules, so we don't have a repetition rate limit. The other question was protons. Yeah. Okay, so as you go to heavy massive particles, the spacing of the gradient teeth has to be compressed. And so it makes it much harder to accelerate heavy particles. We've not given it serious thought on how we might do that. We have the ability to choose any wavelength within the transparency range of a dielectric. So we might take something like gallium arsenide and work out at 16 microns with the wavelength, and then run the structure size such that we're phase matched for propagating heavy protons over some reasonable distance. There's a need for that. We know there's applications for that. We just haven't had the time to go explore it.
Red microphone, Bob Terry. And then we'll take one from the web, and then we'll go to the blue microphone.
Okay, so I can remember, Bob Terry, member of the society. I can remember years ago working with traveling wave tubes.
Yeah, I know about traveling wave tubes.
And traveling wave tubes now look like they just become tinier and tinier and tinier.
That's right. Yeah.
This is fully with field-bounded conditions and no matter. So it's similar in that sense.
It is.
What can you, if you can move protons, other heavy particles like deuterons maybe, do you think you can find a way to control the deposition depth from your array so you can tune where it goes into a gas to produce ionization to
yes. In fact, we do that with electrons, and electrons in some sense are nicer particles. They're more gentle than the protons that are piling up at near the end of their absorption path.
What sort of maximum gamma factors do you achieve in these devices?
The way I'll answer it is the electron penetration depth for an MeV electron beam is about 2 centimeters. We can go to 10 MeV and end up with something that's of the order of 5 centimeters in electrons, not protons. The reason we like the electrons is they're easier to handle and deliver. And they don't cost a whole lot of money to make. We're now getting them off of a silicon tip for next to free, right?
Yeah.
So we're not sure how all of this is going to work out. We do know our very first meeting with the medical company was Very and Associates, and we asked the director of research at the company, George Stasiak, if we could build an accelerator that could fit in a catheter and you could put it in the body, would that be important for what you do for patients? And he said, if you can build an accelerator that can be put in a catheter, it would revolutionize radiation in medicine. And what he meant by that is you don't have to do conversion of electrons to X-rays and go through the skin and go through the body and rotate to get you literally put the electrons where you want them and only where you want them, and you tune the energy so the stopping power is exactly right. Okay. And that's what we think we can do. That may be the first application that we actually work toward, because we don't have to do much to our current accelerator structure other than operate it. It's already got the average power required to deliver the grays you need to make the process work.
Thanks very much.
Do we have a question from the web?
We do have a question from the web.
Oh, we have a question from the web.
Yes, a question from the cyberspace is coming to you. From
Christine is watching on YouTube, and Christine asks, or she observes, you made an important point about how long research like this takes. In a competitive funding environment, how do you get sufficient attention to ensure funding across time, government administrations, et cetera?
Yeah, that's a great question. We all live in the environment with instability. And every once in a while in your research programs, you get lucky. And I remember my first big NSF project was under Research for National Needs, the RAND program. And the person who managed that program had a long-term view of what it meant to do research and make remote sensing with lasers a practical technology. And that was a gift because we didn't have to go write proposals every year, and we didn't have to up our ante to try to keep funded. But it's not often you find people like that. A second one I already mentioned is Howie Schlossberg. He was famous in the laser community for funding some of the best laser research ever, but he had a long-term view about it. He wasn't after results tomorrow. He was after results that lasted decades. So other than that, all I say is every once in a while, if you make yourself known, if you talk about your research broadly, somebody in the audience who can do something with you or for you will raise a hand and say, hey, can we talk? I mean, that's how Gary Greenberg got in touch with us. He heard about our work, saw that we'd been successful, and that we had been unfunded. I mean, the government basically unfunded us. And he said, you know, the Moore Foundation likes to fund research that's high risk. I told him that accelerators was very high risk. And he said, what we'd like to do is make sure you can do some science at the end of it. So he actually funded us to do these applications, to begin to look at them and design the accelerator to meet the applications. So when you get lucky, say thank you to your sponsors, because every once in a while they do more good than they know by allowing you to do research that takes longer than they think it might have to take.
Okay, we'll have the blue microphone and then the magenta microphone. So Bob, blue microphone.
You had mentioned one possible application where your system works a lot better than the standard big accelerator. Do you have some other ones you can tell us about?
Well, the moment that we can take an accelerator and bring it into the laboratory, we've already made a major step forward. Our electrons come from an apparent spot size of 1/10 of a nanometer. That's an atom. So the focus of our electron beam is back down to an atomic scale focus. So instantly we can think about electron microscopy. And since we have control of the energy of the electrons, we can control the penetration depth. We can control the resonance interaction of the electrons with matter in the microscope. So that's just waiting there to be picked up. That's one of those lovely fruits on the ground that you walk by and pick up. And so I hope we have a chance to do that before the end of the Moore program in maybe a year to 2 years. Yeah. But it's this. My analogy that I've used, which is pretty close, is that in the laser business, we went from gas lasers and glass and vacuum pumps to semiconductor lasers, literally in the 3rd year after the invention of the laser. It took a decade before the semiconductor lasers were at room temperature, but today they are the most efficient laser radiation we know. 70% electrical efficiency is the efficiency of a diode laser at 800 nanometers. So that's more efficient than the best klystron. So that alone tells me there will be applications in this arena that we haven't even thought about yet, because we're opening up a whole new window by which I could use electrons to probe matter and understand matter. My colleague Jim Harris, who's a faculty member in the EE department, says, you know, my whole life I've spent trying to corral those darn electrons that are running around like Boltzmann particles, and they never get together, they never go where I want them to. For the first time, I have control over them. I can send them down the pipe when I want to. I can modulate them in time the way I want to. And we haven't talked about spin, but we can do spin polarization studies as well. So I think we're on the cusp of where we're getting the takeoff point where people see value. What we do to help is we send structures off to our colleagues. We've sent structures to Israel, for example. They then use their electron beam and pump them and begin to do their experiments.
Magenta?
Yes, my name is Bruce Kane, and I'm a member. My question is friction loss. If you have your electron beam in the neighborhood of materials, there has to be loss. So you keep talking about gigavolts per meter acceleration. If you turn off the acceleration, how rapidly does that energy get lost? And is that going to limit your energies that you can accelerate to?
Yeah, that's a good question about a loss. There are different kinds of loss that we keep in mind. One of them is radiation losses into the accelerator structure. It back reacts. And so I remember when Tyler Hughes was doing his calculations on his coupling to the accelerator, he had designed an accelerator so efficient that the computer program would walk up to an edge and then just die. And he said, "What's going on?" I said, "Have you thought about radiation?" And he says, "Oh." So he turns around, puts in the radiation term, the accelerator runs up until it's an efficient radiator, and then all the energy goes out as a free electron laser in a radiation mode. So there's a way in which you get loss that's reactive in the medium, right? And you have to pay attention to that. And the other kind of loss you get is wake field drag loss. My electron is going down this 400 nanometer channel. The image of that electron on either side is dragging behind it. And that's a loss. That's an ohmic type of loss that you have to pay attention to. So we haven't seen that so seriously yet because we haven't yet put 1,000 particles in a microbunch. We put 100 particles in a microbunch. So the wake field drag that we would get is not so severe yet. Okay. Are there other kinds of losses? There's one that's helpful to you. The cross-section of an electron interacting with an atomic medium inside of a cell is about 4,000 times higher than the cross-section for an X-ray interacting with the same matter. That factor of 4,000 is huge in biology. It means I'll be able to do electron microscopy in cells with much less electron current and heat and still get a good interaction than I will with a hard X-ray laser. So there's an area where the electron properties are giving you an advantage over an X-ray laser that might focus to the same spot.
We have a question in the back. That's the red microphone, I believe.
Hi, my name is Brett Magrum, and I'm a member. Sorry. Lasers, microchips with lasers on them allowed obviously for CDs and DVDs. And I guess my question is a data storage question. Have you probed, if we could have an accelerator with a beam of electrons, the data storage on a medium could be, probably millions of times higher than with a DVD with a laser light. Have you done any sort of data storage tests, that you could do with a, accelerator on a microchip?
That's a great question. The answer is no. There's no one that I know about in our research grouping of people from EE and computer science and the rest that have raised a bell and said, hey, we ought to think about data storage. So we haven't explored that idea at all. But we have continually rated ourselves relative to the brightness of the electron source that we use to illuminate our accelerator. And our silicon tip is still one of the brightest electron sources we've seen. And if that's the case, and if we learn how to keep it stable for hours and weeks and months and years, then we'll make a major impact on the use of electrons in structures like you suggest, where the physical spot size and the location of that spot is your data storage mechanism.
If there are no more questions, well, there are a lot of questions, but you're going to ask Al. We need to get you a microphone. Please stand up.
This is not really a technical question, but my name is Al Ehrlich. I'm a member. This isn't really a technical question, but you sort of teased us with the idea that DARPA just cut you off for no special reason. Did they ever provide a rational reason or any reason at all?
Well, we knew that the program director was leaving to take a position at MIT. And so one of the difficulties we faced is the program was already about ready to be cut by DARPA, and the only person in DARPA that could stand up for it was leaving. So that made it a pretty soft spot for DARPA to go ahead and cut it. I've dealt with DARPA before, so this wasn't a surprise to me. It was just interesting that they had invested some funds and we had made some spectacular progress beyond anything we thought we would do.
So
And
it was just a cut of
they didn't
convenience.
value that very highly.
They just cut you because they had to cut something? And
Yeah, they had to cut something, and if your program manager's on his way out the door, man, that's easy. There's a set of programs
No,
like
you're right, I've seen that. Okay.
Yeah.
Why do you think they were interested in the first place?
Why did they want the?
Yeah, DARPA. What
Oh,
was
we
their
know why
interest?
they wanted it. They wanted to do medical procedures in the field with a small X-ray source. We have the ability to build an X-ray source that fits in your pocket, and if you want to have emergency surgery or emergency inspection, you'd love to have a small X-ray source in the field that you could use. Commercially, there's a similar market. It's called doing pipe X-rays for strain and breakage and fractures in piping. And if you have a small, very small accelerator, you can do that kind of work with one person on time and do it quickly.
Any other questions? Frederica, you want to ask another question? We got to get you a mic. Wait. Can we use a different mic than that one? That one's pretty poor.
Well, you know, a major application in the Air Force is detecting cracks and material damage in aerial platforms.
Right.
And a kind of another array kind of infrastructure that you can scan it, and you can, in a sense, even instrument it into the platform, so you can do it when the airplane is
Keep the
flying.
microphone
I
in your
think
mouth.
that may be a great application.
Yes.
So maybe that's you need to discuss that with the Aerospace Directorate. So
So the question was, you know, one major potential application is to inspect for cracks in aircraft skins or aircraft bodies. I agree with that. That's what's being done with the pipes in the field. I know a little bit about the cracks because we do laser removal of paint from airplanes. A little startup company in San Jose uses a Q-switch laser to remove paint without touching the aluminum and without removing the chromate layer on top of it. You can remove the paint on the outside. You can then inspect for cracks chemically and by fluorescence, and then repaint. And so the idea of using a laser depainter and a laser painter for aircraft is now catching on, finally. Boeing has now licensed the company to treat any aluminum-skinned aircraft in their fleet. So it took a long time to get to that point.
We need a microphone. There's an audience out there. It's the red microphone.
Is to, in a sense, have models also that they accept this data, and then you can, in a customized way or in a targeted way, look and detect for cracks in real time.
Yes.
So I can talk. We can
Okay,
talk
good.
a bit
Yeah,
afterwards.
please communicate that.
Well, that's a good note to stop on. Prospective money coming your way. So thank you very much, Bob, for coming here and sharing your time with us. Before you go, I want to present you with a small token of affection and gratitude, and that is a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington.
Oh, thank you very
Covering the
much.
first year or so of the Society's existence, explaining why it was founded, who founded it, and presenting some of the results of the first meetings. I think you'll find a very provocative article in there on how to calculate pi to 30 places.
Sounds good. Larry, thank you very much for all of your help in pulling this together and for bending over backwards to accept a live speaker and not a
Well, we're very glad that you were anxious to or enthusiastic about coming here.
Well,
It's
you were right.
good for us to get back
the crowd
together.
was engaged. They were asking good questions, and it made it a lot of fun. Thank you.
And there are a lot more people online. And the first week, you should have a couple of hundred watching your video. By the way, if you're interested in the coherent light sources at SLAC, we had Persis Drill here a few years ago, and she gave a talk on the LCLS. Is that right? I always forget.
LCLS, yes.
Yeah, the LCLS.
Yeah, laser linear. Yeah.
And I guess she was involved in the upgrade, which I think just got turned on.
It's just being turned on right now,
Yeah.
and so that will be a higher repetition rate device based upon a superconducting accelerator driver. Right.
Yeah, I think she went on to be provost, but I don't know if she is provost anymore.
It's Drell.
Persis Drell.
Provost. Yeah, she is provost
She's
still.
provost.
Yeah, tough time to be provost of any university with COVID.
No, she's that kind of person.
Yeah,
So
yeah.
if anyone can handle it, she can.
Good.
All right, so before you go, we're going to talk a little bit about what's coming up. The next 2 lectures will be in person. The fall lecture series has been posted to the website. And the next speaker for the 2,450th meeting will be on Friday, December 13th. And the speaker will be Francisco Cordova, director of the Arecibo Observatory. And he'll be speaking about the observatory's history, including that precedes its untimely demise and its prospects for the future. And I think in this graphic presentation he sent me, you can see one idea for the next generation Arecibo telescope. And the meeting was to have coincided with PSW's DuPont Summit, but PSO has postponed the summit to 2022, not so much because of COVID, but because their meeting schedule has been so successful, they had to cut back a little bit doing hybrid events. The 2,451st meeting will close the fall lecture series on Friday, December 17th. The speaker will be Sean Andrews, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, and he will be speaking on the current understandings of the processes of planet formation, both around our sun and around other stars. Please join us for these meetings. Before we go, let's thank the many people who helped put this meeting together. Cameo Lance, tonight's room manager. Thank you, Cameo. Ann McQueen, Mark Clampin, and Brett Magarin for handling the check-ins. Our live chat coordinator and Rosette boss, Ann McQueen. Jared McQueen, Robert Thompson, and Noah Block for operating the cameras. Our mic runners, Cameo Lance, Lloyd Mitchell, and James Heelan. And PSW's magician of all things, stream director and equipment boss, Robin Taylor, is hiding back there behind the audio rack, the sound board, and a lot of equipment. And equipment handlers, Jared McQueen, Robert Thompson, Cameo Lance, and James Halen, our recording secretary, for writing and reading the minutes of the previous meeting. And with that, I will now adjourn the 2,449th meeting of the Society. I wish everyone a good morning, afternoon, evening, or night, as the case may be where you are presently located. And to those of us here in the Powell Auditorium, to the social hour. The meeting is adjourned.